Okay, so let's get started. So, here's what we are going to do today. So I'm going to talk about this memory performance thing using the slide. And yeah, during the Jupyter notebook in time. And this week I'm actually clearly a little behind. So this Jupyter notebook is still sort of half-baked comparing to what I like to teach you using this slide. But I'm just hoping that it's still useful. So I'm probably make a follow-up another Jupyter notebook after this. So sorry for the remote folks. So the Zoom is suddenly disconnected. So yeah, I quickly realized that it is gone. So I didn't speak much in while. Okay, so let me start over again. So okay, the thing we were talking about in the last week is so there's so many algorithms that whose performance is actually determined by the memory performance, not necessarily the processor's performance. And as an example, I discussed this sparse matrix vector multiply. So, for example, if the total matrix size, which is essentially the number of non-zero elements of the matrix, is much larger than the cache. So these elements must come from the main memory, right? And the performance is therefore actually upper bounded by the number of elements you can bring to the processor from the main memory, right? So if you do a simple back of envelope calculation, where it says, okay, we need to have the memory bandwidth of something like this, 512 gigabytes per second per core, when the actual more realistic number is something like, well, something like 100 gigabytes per second per the entire chip. So it's not a single core, the entire chip. So it's far from what we need if we like to get the sparse matrix vector multiply done with the full processor speed. So this is simply not possible. But the main takeaway here is you have to be very much aware of the memory bandwidth when you are talking about the performance of your algorithm. It's not determined only by the processor's performance. So this week I'm getting into the more performance aspect, not the algorithmic aspect, so more computer architecture aspect. So let me start with the organization of processors, caches, and memory. So how all these things are organized physically. So probably you suddenly know something like this. So you have memory, which is outside the processor. And inside the processor, let's imagine this is a single processor core. So you have a small piece of memory inside the processor that is called a cache. So you have caches which are within the processor and can access much faster than the main memory. And the memory outside the processor itself. So you almost certainly know something about this. And more recently, this cache is making a hierarchy. So it's not only a single cache. So there are multiple levels of caches. So here, I'm just illustrating a hypothetical processor which has two levels of caches. So this is presumably the level 1, which is faster but smaller. And you have second level cache, which is slightly slower but larger. So this is more, in a way, more realistic picture of what the processor actually looks like. And you have multiple cores in a single chip. So you have multiple of what I just described in the last slide. So each one is a core. And each core has multiple levels of caches. And typically, there's something called the last level cache, or typically the third level cache, that is shared among multiple cores within a single processor chip. So typically, it does not necessarily have to be the case, but typically it is the case that this third level cache is shared among cores, but much larger. And there's a main memory connected through, so conceptually directly connected to the level 3 cache. Okay, so each core has its private caches, typically level 1 and level 2 caches. And cores in a chip share a single cache, typically the level 3 cache, and the main memory. And to make the picture slightly more realistic, closer to the actual processor, well, actually there are multiple, something called the virtual cores within each physical core. So there is a very complex relationship, sharing relationship, who is sharing what. So basically virtual cores within a single physical core share these level 1 and level 2 caches, and all cores in a single chip typically share the last level cache or level 3 cache, and the main memory attached to it. Okay, so by the way, this hardware thread is actually synonym of the virtual core. And yeah, even more realistically, each server node has multiple chips, typically 2 or 4 and up to something like 8 in the maximum. So each one looks like what I have just described in the last slide. And each chip has its own so-called local memory that is somewhat closer to the typical, the particular chip. But nonetheless, actually, all the memory locations, memory so everybody can access at any address of the entire processor memory. And this is what I said. So this is what typical single compute node looks like. So the top of the hierarchy is the entire node, the motherboard. You have multiple sockets, and each socket has multiple cores, and each core has multiple virtual cores, and the multiplication factor are something like this. So the number of sockets in a single board is typically from 2 to 8. The number of cores in a single chip is nowadays slightly bigger. So something like, well, 2 is nowadays rare. So something like 4 to 38 or 60, 64, something like that. And a virtual core, in the typical Intel configuration, it's almost always 2 or 1. But other vendors like IBM are making processors that have up to 8 virtual cores within a single core. And okay, so L1 and L2 are physically attached to a single physical core, and the size is typically, so L1 size is typically something like 16 kilobytes to 64 kilobytes per physical core, and L2 size is typically something like 256 kilobytes to up to 1 megabyte. And L3 is actually much bigger, partly because it is shared by so many cores. So it doesn't make sense if it is not as large as the L2 cache size multiplied by the number of cores. So it's well, discontinuously much bigger than the L2 size typically. So this is the typical numbers. And well, details aside, so in terms of the speed, L1 is faster than L2, which is faster than L3, which is faster than main memory. And in terms of the capacity, the opposite is true. Otherwise, it doesn't make sense to have this kind of hierarchy. So this hierarchy is made precisely because, well, it's difficult to make a cache that is both faster and larger. And each cache holds a subset of data in the main memory. So in terms of the set of the data that are hosted, well, this condition typically holds, almost always holds. It should almost, sorry, it should always hold. Typically, but not necessarily. So that's, well, especially recently, it's not necessarily the case, but typically it used to be the case that L1 is included in the L2, L2 is included in L3, and L3 is included in the main memory. So when data is in the L1 cache, it is always also in L2 cache. Yeah, something like that. But well, actually, this is not necessary. And well, especially in terms of the relationship between L2 and L3, it is somehow less typically the case. But details are not super important. So what is important is how you reason about which subset of data will be in the cache. When the processor is actually doing all the management on behalf of you. So you don't have to say, okay, I want to bring this data in this level of cache. So it just automatically happens when you access the data using the ordinary load instruction. But as you're going to see, in terms of the performance, the cost of accessing data is very significantly different depending on which level of the cache the data happens to be in. So when you reason about the performance of your program, you have to reason about which part of your data will be in the cache. Of course, you cannot predict it completely, but you can still make sense of it. So this is important. And this can be made sense of by learning how cache manages its data. So something called cache management policy or cache replacement policy. So this is the basics of the cache management or replacement policy. So a cache generally holds data in recently accessed addresses, so up to its capacity. And this is accomplished by something called the LRU replacement policy. So LRU stands for least recently used. So least recently used replacement policy, or its approximation. So it's not exactly LRU, but it's more like an approximation of it. So namely, so every time when you execute a load or store instruction and it misses the cache, so that the address you're accessing happens to be not in the cache, then the processor has to bring that part of data in the cache. And as a result, that the processor needs to evict or replace some data from the cache. And when you're doing so, that the processor basically replaces the least recently used data in the cache. That one will be replaced. So this is the replacement policy called LRU. So with that in mind, so here is a very crude approximation of which part of the data will be in the cache at any time during the execution. So the crude approximation is that, for example, data in 32 kilobytes L1 cache will be most recently accessed 32,000 distinct addresses. So that's I'm going to make it more precise down the road, but this is the approximation 1.0. So the most crude approximation. If the cache size is 32 kilobytes, so which 32 kilobytes is in the cache? It is data you most recently accessed. 32 kilobytes, up to 32 kilobytes of data you most recently accessed. So this is what is in the cache at any given point of the execution. However, due to implementation constraints, the actual caches, real caches are slightly more complex. So I'm going to make this picture gradually more precise down the road. So this is a picture of cache in terms of something closer to the actual implementation. So the first thing you have to know is the notion of cache line. So when the cache is, for example, having the size of 32 kilobytes, well, it's actually not the 32 completely arbitrary addresses. Sorry. So it's not arbitrary set of 32,000 distinct addresses actually. So a cache is organized as a set of fixed size lines. So what is called lines. So this is called a cache line. And a typical single line size is 64 bytes or 128 bytes. So in most, if not all, but as far as I know, all Intel processors have a cache line size of 64 bytes. So what is the cache line? So it is actually the minimum unit of data transfer between levels. So when the data moves from one cache level to the next, or the main memory to the cache, it always moves at least in the unit of 64 bytes. So it doesn't move a single byte from the main memory. And it is also the minimum unit of replacement, right? So when you access, for example, a single byte of data, well, it still brings the entire 64 bytes containing that particular byte you're accessing. And the entire 64 bytes will replace some 64 bytes in the cache, the least recently used line in the cache. So here's the actual, the picture somewhat closer to the reality of 32 kilobytes cache with 64 bytes line. So it is actually 12 lines, each line having 64 bytes. So it's different from the cache that is able to have 32,000 arbitrary addresses, right? So it can only have 512 64 bytes contiguous data in the address space. So this is what the real cache looks like. So here's the slightly more accurate description of which data is in the, let's say, 32 kilobytes L1 cache. It is most recently accessed 512 distinct lines. So each line is 64 bytes of consecutive addresses. Okay. So you have to know 64 bytes is the minimum unit of data transfer and replacement. And here's another element that makes the picture slightly more complicated. So it's in a simple program you can pretty much ignore this thing, but at times you still have to know about this. This is something called the associativity of caches. So how to explain? So the free associative cache, full associative cache is something that is very close to what I have just described. So in the sense that these lines are precisely most recently accessed, let's say 512 lines, if the entire size is 32 kilobytes. So in terms of the implementation, this means that a block can occupy any line in the cache, regardless of its address. For example, when a line, the 64 byte blocks needs to be brought in the cache, in this free associative cache, the processor finds the least recently used line in the entire cache and replace it with the item that is just accessed. This is free associative. And in the free associative cache, what is in the cache is precisely the most recently accessed whichever number of lines in the cache. The opposite extreme is something called the direct map. So a block can enter only at its own designated seat, or in technical term, it's called a set. It is determined by its address. So if this block has a particular address, from the address, the line it needs to go is completely determined by its address. So no matter whether this is new or old compared to other lines in the cache, this guy has to be evicted and this guy has to be replaced. So this you can imagine, as you can imagine, this simplifies the implementation. Right? The processor doesn't search the entire cache to know which lines is the oldest, right? So this is in a way, a very crude way of making a cache. But nowadays it's rarely used. But still, it's instructive to know that there's a direct map method in the design space, in the entire design space. So K-way set associative is the more like the real cache. And as you can easily imagine, it sits somewhere between free associative and direct map. So each block has some number of seeds or sets it can enter, but it is determined by its address. So for example, given the address of this block you want to bring into the cache, well, the address determines, okay, so this guy can be seeded in any of the lines here, the color here. And the processor chooses whichever is the oldest among these lines in this colored region. So this is a K-way set associative. If the number of lines it can be seeded is K, it is called the K-way set associative. So in terms of the set associativity, direct map is a one-way set associative cache. And the full associative cache is the infinite way set associative. This is one way you can put it. But I guess more precisely, this is the total number of lines in the cache. This is free associative. So we can liken it to the office having the free address. So in free associative cache, so it is a complete free address office, right? So in the free address office, you have so many seats. And when you enter the office, you can be seated at any seat you want, right? So as long as it's free. In the case of cache management, you have to kick somebody out before you are seated in the seat you are seated. But in the free associative cache, it's a totally free address office, right? And direct map cache is somewhat like it's free address, so you do not necessarily have your own reserved seat, but you can still be seated only one particular seat designated to you, right? And when you enter the office and somebody is in your seat, then you have to kick out that particular guy. So even if there are other seats available in the office. So K-way set associative is obviously there somewhere between. So you have K seats, you can be seated. So this is the associative. And here's the example cache organization. So this Ice Lake 8368 is the one we are using on the cloud environment you are using the Jupyter. So its level 1 cache has a capacity of 48 kilobytes per core, and associativity is 12. And L2 cache is, I think, I'm not 100% sure, but just a quick Google search. It looks like it has 512 kilobytes per core, and it is a reasonable number. And presumably the associativity is 8. And L3 cache is much larger, which is 57 megabytes per socket. And actually, there's a Linux command that can tell you the cache organization. But due to some virtualizations that are happening in the cloud environment, this tool seems to be showing some bogus information. So I'm not completely sure. But I think these are the numbers we have in our environment. And then there are some earlier models like Skylake and Ivy Bridge, but they look pretty much similar. And especially this line size is always 64 bytes. Well, of course, these details are not important, but when you talk about the performance, and for example, when you try to make as much data as possible in, for example, level 1 cache, well, it's important to know the level 1 cache is that small. We are not talking about a few megabytes of memory. So it's just a dozen kilobytes of memory. So this is something and you have to know. And so why this associativity is important in practice? So the associativity makes things more complicated. And if the cache has a large associativity, then you don't have to worry too much about it, actually. So it's in a way closer to the free associative cache. And free associative cache can be approximated by through the LRU policy. But you still at times have to be aware that the cache is a limited way associated. So in practical terms, I will explain why later, but in practical terms, this is the thing you have to remember, which is you have to avoid having addresses used together a large power of 2 bytes apart. So when you have some set of data, some number of data, if the distance between your 2 addresses is a large power of 2 bytes, then you are getting into trouble. I will explain later why. But this is something you want to remember. And the actual situation in which you have to be aware of this is when you have a matrix or multi-dimensional arrays with a large power of 2 number of elements in large power of 2 number of columns. Yes. So you want to avoid making a matrix with a large power of 2 number of elements in a single row. In other words, a large power of 2 number of columns of the matrix. So this is a common mistake. So when you, for example, experiment with matrix multiplication, it is somehow tempting to make the size like starting from, let's say, 64 columns. Next is 128 columns. The next is 256 columns. we are all tempted to do something like this, but actually this is a very bad for performance for the reasons I made clear shortly. And another thing is, another situation in which you are tempted to do something like this, but in fact you have to avoid is to manage your memory by chunks of large power of 2 bytes. So this is another thing many people are tempted to do. For example, when you manage your free space or free memory space, even if the requested byte is, for example, 40 bytes, or you say, okay, so make it just power up to 64. And even if the requested size is, for example, 100 bytes, you make it 128 bytes. This actually makes the management simpler, but it is actually not a good idea. And the last thing, which is very common when the students who learn the performance things for the first time is to do all the experiments with numbers all a power of 2. So it's very common to change the size of the data from very small to large. And again, it's very tempting to do it like starting from 64. The next number is 128. The next is 256, all the way up to a very large number, a very large power of 2. It is generally a bad idea. It is a path to surprise or sometimes a disaster. So why is it the case? So actually, data whose address is a large power of 2 bytes apart tend to go to the same set, and conflict misses tend to result. What is the set? The set is this one, right? And if many data are actually mapped to the same set, but other sets are simply wasted, right? And if this is, for example, this picture is a 4-way set associated cache, and even if you have only 5 elements, if all these 5 elements are mapped to the same set, and you cyclically access these 5 elements, when the cache misses starts to happen, because you have only 4 seats available for these 5 data elements. So here's a more detailed explanation about how conflict misses occur, but I guess I can skip it and leave it to the Jupyter exercise. The Jupyter notebook does not necessarily explain all of these mechanics, but I guess even if I explain it later, I think you better play with the Jupyter notebook first. So let me skip it for a moment. And okay, so here's take away so far. So you want to understand which part of the data you are using will be in the cache. And the cache configuration can be described in these 3 parameters typically. So one is the total size, C, and the line size equals Z, which is almost always 64 bytes. And associativity being K. And the approximation 0.0, the first very crude approximation is, okay, just so we only consider the total size. we ignore even the fact that data is always transferred in the unit of cache line and replaced in the unit of cache line. So effectively, we simply assume z equal 1. And associativity, we assume it's infinity, a free associative cache. In this approximation 0.1, 0.0, the data in the cache is precisely most recently accessed C distinct addresses. But even this crude approximation sometimes helps, and it's sometimes sufficient. Making it somewhat more realistic, the approximation 1.0 is aware of the cache line size. So instead of modeling the cache as the C distinct addresses, it models the cache as a C over Z distinct lines, distinct Z byte of block. This is the approximation 1.0, and we still assume that it is free associative. So it's totally LRU in the entire cache. And approximation 2.0, it is pretty realistic, then consider associativity too. But yeah, sometimes very complex. So you have to take, oops, the Zoom is again gone. Can you guys hear me? Oh, okay, it's still connected. Okay, sorry. I thought it's gone. Let me make sure it's not gone. Okay, so yeah, I think it's not gone. Okay, so when you take into account this associativity thing, you have to take into consideration the strides between addresses you are using. So the strides between data items you are actively using. And you have to be aware that, okay, so these sets are all mapped to the same set. So you have to make the number of items mapped in the same set smaller than the associativity. This is how you reason about cache replacement considering the associativity. So depending on your situation, you're going to use sufficiently accurate, but the simplest model. So in the Jupyter notebook, you are going to experiment with the caches, and you're going to measure the cost of accessing data from a particular level of caches and all the way to the main memory. And yeah, let me spend just a few minutes on describing how you can do that. So I'm going to talk about how to assess, how to measure the cost of data access. So what we like to do is to obtain the cost to access data in each level of the cache, as well as the main memory. And we are interested in two aspects of the performance. One is latency, and the other is bandwidth. Just like we were interested in latency and throughput when we talk about the processor performance, right? So latency is the time until from the time that something starts until the end. So in the case of memory access, the latency is the time until the result of a load instruction becomes available from the point that the load instruction is started execution. The bandwidth is the maximum amount of data per unit time, for example, the cycles or second, that can be transferred between the layer in question to the CPU, from the L1 to the CPU, from the L2 to the CPU, or from the main memory all the way to the CPU. So this is the bandwidth. So even if the latency is very large, if the processor can execute multiple such load instructions in parallel, then you may obtain a good bandwidth, right? So this is the situation is pretty close to what we discussed about the FLOPS performance, right? So one FMA has a latency of 4 cycles. So if you are doing only a single FMA at a time, then the maximum throughput you can obtain is just 1/4 FMA per clock, right? But you can execute multiple FMA instructions concurrently, and until you hit the throughput limit of the performance, the throughput limit of the processor, right? So pretty much the same thing happens when we talk about the memory access performance. So individual memory accesses have so much latency, but you can do many of them at the same time concurrently inside the processor. This is how you get the bandwidth. And this is how to measure the latency. So you prepare an array of n records on n cells and access them repeatedly and measure the time that it took to complete a large number of accesses. And in order to precisely measure the latency, you want to make sure that these load instructions are dependent on each other. So if you simply issue so many load instructions, but the processor may be able to execute them in parallel, right? So the effective latency becomes much smaller than the real latency. So in a way, for the purpose of measurement, of course, for the purpose of getting better performance, it is a good thing. So you simply issue load instructions in the instruction stream, and the processor is able to execute many of them in parallel. That is definitely a good thing for the purpose of getting good performance. But for the purpose of precisely measure the latency, it makes the picture somewhat obscure. So you make sure that a load instruction depends on the result of the previous load instruction. So you issue a load instruction, so you get some result back, and use that result to determine where you want to access next. So this is how you can precisely measure the latency. So in other words, you make sure that no multiple load instructions happen at a time. So this can be done by something like this. So you have a pointer, and you access an element through this pointer and get the result back. And in the very next iteration, you use that result to determine which address you want to access next. So the Jupyter Notebook is doing essentially the same thing in a slightly different way, but what it is trying to do is exactly this. So in the illustration, it looks something like this. So this is the first cell you're going to access, and you access the next field of this element to get the next element you want to access. And you access the next element of this cell to get the next save you on access. So something like this. So what the program precisely does is explained in the Jupyter notebook again. So with that, I think I want to give you the time to work on the Jupyter notebook I have just gave. So this PD10. So let's have some exercise time until 6. And meantime, of course, you can ask a question on this and the other thing. Okay. So let me start again. So let me explain a little bit what I want to tell you with this. So basically, yeah, this is the actual experiment of what I have just explained in the slide. So well, it's conceptually a very simple thing, but I think a few people actually do it and witness what the actual memory access cost looks like. So I hope that so you will understand it and you will have some fun doing this by yourself and witnessing it by yourself. So the program is trying to measure the latency by, well, essentially doing something like this, as I have just explained in the slide. But well, actually, it's doing almost the same thing using a slightly different way. But what's actually happening at the machine instruction level is almost the same. But it uses the K as the index to choose a particular element of an array, and use that value to list the next element in the array. So you can understand that there is a dependency between two back-to-back load instructions accessing the array elements, right? Because K that is brought from the memory, the array, is used to determine the next element to access, right? So this way, we make sure that there are no multiple load instructions going on at the same time. And yeah, this is the actual program you are compiling. So it's exactly, or simply repeating this, right? And this is simply a measurement code. It first creates an array of A, I have just shown, and initialize the element in such a way that this loop, sorry, getting back to this. So this loop, yeah, is accessing all or part of the elements of the array repeatedly. So n is, for the purpose of measurement, n is made very big, but it does not necessarily mean the array is that big. So the array may be small, so that, for example, we can measure the performance, the latency of, let's say, L1 cache. In that case, we will make A smaller than L1 cache. But still, we make this n very large. So what actually happens in array A is, well, it simply repeats accessing the array many times. So actually, this K forms a cycle. So if you repeat doing this, well, at some point you just come back to the initial element, and you simply repeat the same access patterns many times. So this is what actually happens. So omitting the details about the measurement code. So you simply compile both this main function and the actual scanning code. I'm just using G++ and execute it. And this command line, for example, it's probably different from what I have just given to you. So it was originally, I think, something like this. So what it does is, okay, so first, it creates an array of 16 kilobytes. So this is the array size in terms of the bytes. And this is the stride. Stride meaning that AK, so the array A, the element A of K is initialized in such a way that AK points to the element 64 bytes ahead. Right? So it's determines the stride with which you scan the entire array. And A is the number of times you iterate the loop I have just shown. So when you do this, okay, it says the array size is 16 kilobytes and stride is 64, as I just indicated here. And it makes a number of accesses. So it makes 100 million times. It accesses the elements 100 million times. And here's the performance result. So first of all, it shows the number of instructions that get executed. So it's very instructive to see that this number is almost an integral multiple of the number of iterations. So it strongly suggests that the number of instructions per iteration will be 4. So it's almost 4 times larger than the number of accesses, right? So I'm going to see this later. And it's also instructive to observe that the number of core cycles. The core cycles is almost precisely 5 times of the number of accesses, which suggests that the number of cycles per iteration will be 5 in this case. And it also reports the number of L1 cache misses and the number of cache misses. Well, it is apparently talking about a different level of caches. So which level of the cache it precisely it is. It's not described anywhere, but it's probably the level 3 cache. I'm going to see this later. So you can change the array size. For example, this 16 kilobytes is much smaller than L1 cache. So what happens here is that almost the entire array fit the L1 cache. So, and you repeatedly access some elements of this array many times. So in total, 100 million times. But it's not surprising that there are almost no L1 cache misses. So it of course incurs something like 2,000 L1 cache misses, but it's much smaller than the number of times you issuing the load instruction. So effectively you can understand that it is making almost no cache misses during the loop. It's not surprising because the entire array is smaller than the L1 cache. Yeah, so it's instructive to see the assembly code that is generated by, for example, in this case, G++. So let's take a look at the assembly instruction generated, this one. Scan is the function name. So the name is mangled by the C++ compiler, but the scan is the original function name. And the actual loop looks like this, right? And in each iteration, you execute 4 instructions, right? That's precisely why you see this number of instructions executed, right? And you can also understand from this instruction sequence that this move instruction is the load instruction accessing the array element. This is the base address. RDI is the base address, A, the address of A. And R8 is the K, the array index. And this was a slightly complicated. The operand is saying that, okay, use this base address plus 8 times R8. So they generate this address and access this address and get the result to R8. So the next K. And it seems that this load instruction is taking 5 cycles. Of course, we cannot immediately rule out the possibility that other instructions somehow determining the number of cycles it takes per iteration. But actually, if you look at the process spec sheet or LLVM machine code analyzer, you can learn that these instructions have a very small latencies. So we are almost certain that the 5 cycles per iteration is determined by this load instruction. Like this one, right? And so what we get from this experimental result is, okay, 5 cycle is the latency of L1 cache, right? And you change the array size and strive for the reason that becomes clear later to precisely assess the L2 latency or L3 latency or other latencies. And another thing that is sort of interesting is that if you use Crank LLVM compiler instead of GCC, then it actually generates somewhat different code that is apparently more optimized, but in fact it's not. So let me open it again. So this is the code generated by LLVM. So this is the apparently the main loop. So this one apparently looks better than what this is C++ has generated. So it unrolls the loop 8 times. So rather than executing 4 instructions per every single load instruction, it unrolls loop 8 times. So it executes 8 load instructions with only 10 instructions, right? So the number of instructions per load instruction is 1.25, right? So 10 over 8. So if you execute this code, so it precisely tells you the number of instructions is like 1.25 times the number of accesses, right? But what is more interesting is the number of cycles doesn't change at all. So it's not the number of instructions you are executing that matters. It is the latency of the load instruction, which is 5 cycles per load instruction, that matters. So no matter how many times you unload the loop to reduce the number of instructions you execute, the actual number of cycles it takes doesn't change at all. And so what I'd like to expose you with this experiment is, for example, okay, let's increase the data size you're accessing. So for example, let's double it to 32 kilobytes. Then, okay, the number of cycles almost doesn't change. And L1 cache miss is still very small. So let's increase it to 48 kilobytes, which in our understanding is precisely the L1 cache size of this machine. So the array almost exactly fit the L1 cache. So the number of cycles still doesn't change. Well, so we observe some slight increase in the number of L1 cache misses because there may be something else is going on the processor from time to time. But still, it's far smaller than the number of load instructions you executed, right? So let's make it larger than 48 kilobytes. Then what happens? So the number of cycles doesn't change. Well, so okay, so the first thing, so let's talk about this number of cycles later. But the thing you obviously observe is the number of cache misses now become almost the same as the number of accesses you issued, right? So this clearly indicates that the data is almost always missing the cache. And what is remarkable is that when the cache size is 48 kilobytes, we're just slightly so making it slightly larger than the cache size. So making it 52 kilobytes when the cache size is 48 kilobytes. You still observe almost 100% cache misses. So this is this is because the cache is managed with LRU. Like I said, so this program cyclically accesses 45 kilobytes of data. So now, so what we are seeing is that, so this is actually 12-way set associative cache. And each set, you have 13 elements accessed during the loop. So, and this happens cyclically, precisely cyclically. So it is almost always the case that the very next element you're accessing is the least recently used element in each set. So that's why you observe almost 100% cache misses when the data is only slightly larger than the L1 cache. And so why the number of cycles doesn't increase? Well, actually, it's actually not my expectation, but the possible reason is I come to that later. So the one way we make this not to happen is to make the slide larger. But by the way, this is a small exercise for you to change this array size to find the cache size of each level. So here we just witnessed that the L1 cache size will be somewhere around 48 kilobytes. So you can do a similar experiment to find out the L2 cache size and L3 cache size. And here's some visualization program. So you execute it with a range of data size, array size. And this time I'm using the slide of 4096 bytes rather than 64. So the array is accessed with a large stride. The reason why I'm doing this, I'll come to this shortly. And this cell executes us many times. This the same program with various number of array sizes, and the slide is always 4096. And it produces so many result files, and then here's the visualization of the results. So this is the array size in terms of the bytes. And this is the number of cycles taken per access, taken per iteration of the original C program. So the most remarkable thing is that if the array is very large, so it's as large as 100 megabytes or more, 200 megabytes or even 300 megabytes, yeah, the cost per access is very large, right? So it's 2 orders of magnitude larger than the number of cycles per FMA instruction, for example. So you have to be aware of this. So when you talk about the performance of your program accessing the large data, the major cost is associated with the data access, not the computation itself. So when your data is mostly coming from all the way from the main memory, taking something like 250 cycles each time, then it doesn't make sense almost at all to try to, let's say, minimize the number of instructions in your loop or increase the number of FMA instructions you are doing at the same time. So it's not going to happen anyways. And also, you can witness the remarkable difference between the number of cycles it takes depending on the data size, which is depending on where the data is actually coming from. So in this region, the data is apparently coming from the L1 cache, right? So 10 to 4 is 10 kilobytes. So the L1 cache size was 48 kilobytes. So it's somewhere like here, right? So 20, 30, 40, 50. So almost exactly around the 48 kilobytes, the access cost significantly increases. Whereas also it pays in comparison to the cost for the main memory, but still the difference between these two are visible. You can zoom into this. And okay, so the latency to the L1 cache is like something like 5 cycles, which is the same ballpark as the latency of FMA instruction, for example. But if the data is coming from L2 cache, it's apparently taking something like 12 cycles. Okay, so apparently, the next gap is around here. So in terms of the data size, it's something like this is 100 kilobytes, and this is 200 kilobytes, and so probably it's somewhere around 256 kilobytes. So it's tempting to think that this is the L2 cache size because this is the L2 cache hit, but actually it's not. So I was actually wrong. So I was quick searching the web to know the L2 cache size of this processor. So it seems 1.25 megabytes. So it's probably this gap is the gap between L2 hit and L2 miss or L3 hit. So somewhere between 1 megabytes and 2 megabytes. So what is this then? So actually, I didn't talk about this, but it's presumably something called a TLB. So TLB is the what the processor has to accelerate the virtual address to physical address translation. And it's in the worst case, it's done by something called a page table walk, that the processor looks up the data structure on memory to just translate the virtual address to physical address. So TLB is actually the cache of this translation. And as such, TLB also has the limited capacity. And seems like the TLB capacity is 64 entries, and each entry covers a single page, which is 4 kilobytes. So this is what I have just found by the quick Google search. So this is the Ice Lake TLB, and L1D data TLB. Actually, there are 3 kinds of page sizes, but normally it's 4 kilobytes. And it has 64 entries of 4 kilobyte pages, which means that it can remember 64 distinct pages, the physical address of 64 distinct virtual pages. So it covers 4 kilobytes multiplied by 64, which is 256 kilobytes. So this number is actually consistent with what we are seeing here. So the slight increase around 256 kilobytes. So I'm not definitely sure, but probably it's something related to TLB. And probably this is the region in which data hit the L3 cache. And at some point, it starts missing the L3 caches too. So L3 caches, according to the quick Google search, it's 57 megabytes. So this is 10 megabytes. So 20, 30, 40. So the L3 cache is somewhere around this. So the beyond 57 megabytes, it starts seeing the latency of the actual main memory. So the data is coming all the way from the main memory. So you can understand that the accessing data which is in the main memory, not in any level of the cache, is as costly as 250 cycles. So this is the most important takeaway you have to remember when you talk about the performance. And this is showing the L1 cache miss ratio. So if the data is smaller than the L1 cache size, then the cache miss ratio is almost 0. But as soon as it becomes slightly over the cache size, it quickly becomes almost 1.0. And by the way, so it's strange that the ratio, this is the number of cache misses observed divided by the number of accesses, is larger than 1. So it in fact becomes almost 2 at times. It's almost like a 2 or 1. So somewhere almost 2, and in other places almost 1. The exact reason why this is happening is it actually depends on what is counted by the processor as a single L1 cache miss event. But it's presumably having something to do with what is called the adjacent line prefetch. So they actually, when the processor misses the cache on a particular cache line, it brings the next line to the processor at the same time. So I say the 64 bytes the single cache line is the minimum unit of data transfer between different levels of the cache or the main memory. But actually, the processor is doing something slightly more. So it tries to bring two adjacent cache lines at the same time. And the reason why it sometimes is almost 2 and other times it's almost 1. So I still didn't figure that out completely, but I think it depends on the details of the stride and the cache size, and depending on the combination of two numbers, what these adjacent lines, the line that is brought to the processor at the same time with the previous line is used or not before it is evicted. So depending on whether this happens or not, the number of cache misses is exactly the number of accesses you made, or 2 times the number of the accesses you made. And this is the number of L3 cache misses. So the prefetching is another topic that is actually important, and this explains why the number of cycles it is taking, even if the data is coming from the, for example, L2 cache, is different depending on the stride. So actually, this experiment is doing almost the same thing as the previous experiment, except that this time the stride is 64, which is a single cache line size. And this is the it's not visualizing the result. Okay, let me do it now. So actually, when you compare this with the previous experiment, you can easily witness that this one takes much smaller amount of time compared to the previous one. And this is the okay. So this is the comparison between the previous experiment and the last experiment I have just done. So actually, when you zoom into this one, you can actually observe a similar cliff at this point. But the main difference is that, okay, even when you are missing caches, the actual number of cycles it's taking is much smaller this time. And it's clearly coming from the difference in the stride. So the actual set of data you are accessing when you are running that loop is exactly the same. So no matter whether the stride is 64 or 4096. So the difference between them is stemming from what is called the processor's prefetching. And the exact reason is actually described in the Jupyter notebook and also slide. And I don't have much time to get into it now. But well, basically, the processor, so when you are accessing the array with a small stride, so for example, the address X, the next one is X plus 64, the next one is X plus 128. The processor actually figures out that this guy is accessing the array sequentially from beginning to the end. So it is actually issuing, well, load instruction, not exactly the load instruction, but the prefetching much earlier than the program actually does. So the net effect is there are many concurrent, something like load instructions. Many of them are actually prefetch issued by the processor. But something like load instruction, multiple load instructions are taking place almost at the same time. So this is the difference we are witnessing here. And this is probably the reason why we didn't see the increase in the number of cycles when the data it becomes much slightly larger than the L1 cache area. So okay, so I think it's time up now, but I hope that you find this interesting and also understand that this is going to be very important when you talk about the performance of almost any kind of code, even matrix multiply. In the earlier experiment, so you may remember that matrix sizes are made very small. This is exactly because if the data is larger, and then much larger than, for example, L1 cache, then you are going to actually measuring the time to get the data rather than the computation. So that's why the matrix sizes in the earlier experiment were intentionally made very small. Okay, so I think that's it for today. And like I said, this is the last lecture in this year. So in the next year, I'll be giving a lecture by the on-demand video. So you don't have to come here and you don't have to connect to Zoom. And honestly, I don't know when precisely I can deliver the video. So let's please stay tuned. So hopefully around next year, the next week. This time of the next week, but I cannot guarantee you. So I think that's it. So I hope you are having a good end of the year and a happy new year. So it was